Hello, in this video, we will generate the dataset of exponential probability density function. The formula for this is y equals EXPONDIST of x comma lambda comma 0. 0 because this is an exponential probability density function. So let's enter the formula for a array formula for EXPONDIST of the x values, and our lambda will be 3 for now. And our 3 and our last argument 0 because it's an exponent test. And here you'll find the trend line of the dataset and the trend line equation of the dataset. It is 3 times e to the minus 3x, where r squared is 1. This comes in the form of the function of x semicolon lambda equals lambda times e to the minus x. So it's a decaying function. So we can express this using the exponent function, which is array formula, exponent of the x values. Now we have the exponent, and it is 1 times e to the x. We need to have it negative x, so it's negative. Yes, it's a decay. Now we factor in lambda here on the exponent and lambda on the function itself. So lambda will be here. That's our lambda inside. Now we add lambda on the function itself. So that is times lambda. Now we have used the exponent function. The values are exactly the same. So we expect the same results in the the logest exponential regression. We can use Taylor-Maclaurin series sum to generate the approximation dataset of this function. And these values will be the summation of a, the coefficient, times lambda x to the power n, where the values of n starts from 0 to infinity. 0, 1, 0, 1, 2, and infinity. In this case, we can reach 13, our maximum in this because we don't have space. Now we can enter the Taylor-Maclaurin series sum, which is array formula, series sum of the x values, where the power, because there's lambda in it, so we have to multiply this by lambda. There's lambda in it, where the power x to the n, the starting power is 0, then the increment is 1 because it x to the 0, x lambda to the 0, x lambda x to the 1 squared, cube, and so on. So the increment is 1. And the coefficient will be this range, the A column. Now we can work on the coefficients. Is equal to array formula. Let's begin with the denominator. So 1 over factorial of n. Now that we have the denominator, let's continue with the numerator now. So negative 1. So there are two factors, negative 1 to the n, and there's lambda. So negative 1 to the power n. To the power n. Okay. Then we have to factor in the last part of the numerator, which is lambda. So times lambda. Now we're there. So all three trend lines have the same trend line equation except for the last one where there's a slight error, 3 times e to the minus 3.1 x, because this is only an approximation. We can get better accuracy if we increase the value of n and we increase the value of dataset. Now we regress it to the logest exponential regression. So since these two are identical, we'll just choose the original, the blue one. So it is equal to logest data y and data x. I'll show the full statistics. Because we're regressing it against itself, our b0 is 3. Our b1 is, we'll have to calculate for b1, which is our logarithm ln of this value. Negative 3. Our b1 is negative 3. So they're the same. Next, we regress the approximation, which is logest data y and data x. And we show the full statistics. Our b1 will be equal to ln of this value. So we don't get a perfect tree here because it's only an approximation. And but the yellow covers the red and the blue data sets. So this completes the logest exponential regression and the Taylor-Maclaurin series sum expansion of the exponential probability density function.